Welcome back. In the last lecture, we considered various examples, some examples related to Kripke model. A Kripke model consists of a set of non-empty set of possible worlds W, and you have an accessibility relation R, and you have a valuation function with which you assign some kind of values to the propositional variables that exist in your given modal logical formula. So, Kripke is trying to talk about 4 levels of truth. First, truth with respect to a given possible world, and truth with respect to a frame. A frame consists of a set of possible worlds plus accessibility relation. It is an ordered pair which consists of set of non-empty set of possible worlds and accessibility relation, and then a modal consists of W, R and V. So, we have seen so far we have seen various modal logical systems. Till 1960s, modal logicians were working in the tradition, in the syntactic tradition. There they were trying to come up with new theorems by taking these characteristic axioms into consideration. What are the characteristic axioms? Every logical system has its own characteristic axiom, and these modal logical systems are named after some logician or other. For example, in the case of T, T has a particular characteristic axiom which says that it is necessary that P implies that it is P, and for example, if you have another axiomatic system which has introduced before T, that was that already occurred in the branch of deontic logic. The name of the system, modal logical system, is D. D has this characteristic axiom that if something is necessary, then it is only possible that P is the case. So, you have to note that some of the axioms, some of the theorems which are considered to be part of some axiomatic system need not have to be theorem in other thing. For example, if you say it is necessary that P implies that it is actually the case that P, that does not apply in the case of deontic logic. For example, I have been telling you the same example. You ought to follow the traffic rules. That does not mean that you actually follow the traffic rules. So, Kripke just with the help of some relational structures, W or V, it is like a directed kind of graph with which he could talk about many things such as validity, satisfiability, and many things which he is trying to talk about using these relational structures. So, Kripke's main observation is that when you constrain the accessibility relation, then it results in all these different modal logical systems. Suppose if you see here in K has this characteristic axiom P implies Q. It is necessary that P implies Q means it is necessary that P, it is necessary that Q. You do not have to impose any constraint on the accessibility relation. So, that is why it is considered to be the minimal modal logical system. So, the moment you impose constraints on the accessibility relation R, we need to impose a specific kind of accessibility relation on the specific kind of constraint on the accessibility relation. He observed that T, the modal logical system T, has this characteristic axiom. It is necessary that P implies P. This requires that accessibility relation has to be reflexive. So, when it is considered to be reflexive, especially when there are two worlds, let us say you have X and Y belongs to your set of worlds in a Kripke model. If X is accessible to Y, then Y is also accessible to X. If that is the case, then accessibility relation is considered to be reflexive. So, in diagrams it is like this. So, sorry, this is considered to be symmetric kind of property. Reflexivity is like this. So, if X is accessible to itself, then it is considered to be reflexive property. If there is a world X and if this X is accessible to itself, then it is considered to be reflexivity property. So, if there are two worlds X and Y belongs to set of worlds W, if X is accessible to Y, this is the way you write the things, X followed by Y. That means this X is accessible to, this is another world y is x and this is y. Then y is also accessible to x. If that is the case, then you are restricting this accessibility relation to be symmetric, and there are some systems which follow this symmetric kind of if you need to impose symmetric symmetry on the accessibility relation. So then the resulting system could be B or something like that. So like this Kripke could study all the axiomatic systems while imposing some kind of constraint on the accessibility relation. The only thing you need to note is that K does not require any constraint. So all these things we will talk about the same thing when we deal with a particular technique that we are using in this course, that is semantic tableaux method. So what we do is we negate the formula, we will construct a tree for all these formulas, and we see when the branch closes. So now observe this one, if it is necessary that P implies it is necessary that P requires that your accessibility relation has to be transitive, and particular kind of axiom 5 it is that something is possible that phi that has to be necessary has to you need to impose the constraint of Euclidean kind of property. Suppose if x is related to y and x is also related to z, then y is accessible to z. If these two things happen, then y is accessible to z. If that is the case, then it is a Euclidean property. Transitivity property is like this: if x is accessible to y and y is accessible to z, these two taken together leads to x is accessible to z. This is what is transitivity property. Euclidean property is little bit different, that is it looks like more or less like transitivity property, but it is not. X is accessible to y, the same x is also accessible to z, so that is why y is also accessible to z. So x and y, z, z are all these things are possible worlds. So now for example, let us take a simple Kripke structure and see why it does not this necessity of P implies P does not hold in K. You can have a counter example where necessity of P is going to be true, but this P is false. So now let us consider a relational structure where we have two worlds x and y. So now actually it should be like this, P, and here not P is true. Now this x is accessible to y. So now this will serve as a counter example for this one. Why? Because now if you evaluate this thing, necessity of P in all the possible worlds which are accessible to x, in those worlds P has to be true. So this is true, but P is considered to be false here. Why? Because not P is true here, that is why P is false here. So this is true and this is false. This makes the whole conditional false. So now Kripke could easily talk about these things, that the same kind of axiom, if you do not impose any restriction on this one, it is going to be invalid in K, and the counter example is going to be like this. So you can draw a relational structure, and this relational structure will indicate as that is a counter example for this one. So necessity of P is true, but necessity of P is considered to be false here. That makes the whole conditional false. So like that, you can see that, for example, if you draw some kind of if you make this thing little bit different, then that is going to be valid here. For example, if x is accessible to itself, then what will happen in the nearest worlds where P is true, that is the case. This is the nearest world to this one where P is true. In this case, in one world it is the case. So now there is another world which is accessible to itself, x is accessible to itself. In that world, necessity of P is considered to be is false. Why? Because P is false here. P is not true here. So that makes this one antecedent. So I will go in a simple manner. So what we have done is that we have drawn one extra arrow to this one, and then we are trying to see whether it holds or not. So this tells us that X is considered to be, we are using some kind of reflexive relation here. We are imposing the additional constraint that we are drawing it like this. That means X is accessible to itself. So in that case, necessity of P. Necessity of P means in all the worlds which are accessible to this one, your P has to be true. So the world which is accessible from this one is P. In the first case it is true, but the world which is accessible to itself, this is the one in which P is false. That means if at least in one world where P is false, the necessity of P is also going to be false. So for that reason, this necessity of P is going to be false. So now P is already false there. So now we have a truth table for P, Q and P implies Q. So this is going to be false only in this case. When antecedent is true, the consequent is false, is going to be false. In all other cases, it is going to be true. F and F also it's going to be true. So what it tells us is that the same kind of axiom, if you don't impose the accessibility relation, the constraint on this accessibility relation, this is going to be you can have a counter example for this one. So this is going to be a theorem only when you impose some kind of constraints on the accessibility relation. So that is a beautiful innovation of Kripke. He could simply see all the validities etc. of these formulas by means of some kind of relational structures. What all we need is that we need to have some kind of non-empty set of worlds. We need to know how this accessibility relation is constrained, either reflexive, symmetric or transitive or all these things. If reflexive, symmetric, transitive all needs to be there, all are required, then it is considered to be an equivalence relation. And most of the modal logicians were talking about an axiomatic system S5. S5 is considered to be the axiomatic system which is widely studied. Why? Because all these relations are already present in that one. You require reflexivity, transitivity, symmetry etc. That is why S5 is no other system was studied in the sense that the S5 was studied. S5 was studied widely by many logicians, and S5 also later we will see that this S5 will serve as model of knowledge. So that means epistemic logics in particular, we begin with S5. But the thing is that this necessity possibility will behave in a slightly different way. Necessity can be treated as a knowledge operator, and I think that something is possible can be treated as this diamond kind of thing. But in our course we are just concentrating our attention on only alethic modalities, that is we are talking about logical necessities, metaphysical necessity. So we are not trying to talk about necessity with respect to the individual agent etc. So in this way you can have a counter example for in K for T. This axiom is not valid in K system. So in the same way D requires a serial kind of property for any given world. There should always be some kind of world which has to be accessible to that one. So that is what is serial kind of property. And then transitivity property is if X is accessible to Y, Y is accessible to Z, X also has to be accessible to Z. So now based on how you constrain the accessibility relation, Kripke has come up with various modal logical systems. He could clearly say that axiom T, I mean T was defined in terms of characteristic axiom. Till 1960 there was no way to say that they were not talking about validity, semantic, the consequence etc. Many logicians were trying to prove theorems within by using these axiomatic systems. So axiom T will hold just in case the relation is considered to be reflexive, and it will hold just in the case that W is accessible to W. In the same way axiom S4, it is necessary that P implies it is necessary that it is necessary that P holds only when you constrain the accessibility relation to be transitive. E or S5 holds when R is considered to be Euclidean, the one which I mentioned it here, and B will hold when accessibility relation is symmetric. X is accessible to y, y also should be accessible to x. So these are the ways in which depending upon the constraint on the you apply on the accessibility relation, Kripke could find out easily that this is T, this is K, this is K, this is S4, S5, etc. So now what do you mean by saying that some formula is true with respect to the relation structure? What is the relation structure here? W, R and V, non-NP set of worlds, accessibility relation and the valuation function. So you write MW double turnstile phi, that means phi is true in a world W with respect to a model M. So that is defined in this sense. First, any atomic formula if it belongs to any given world is true is represented in this sense. P is true in a world W with respect to a model M. All tautologies has to be true in a given world W, and all contradictions doesn't need follow. That means it doesn't hold with respect to a world W. And not phi is true in a world W means phi should not be true in a world W. If not phi is true in a world W, obviously it is taken for granted that phi is false there. As phi is true, not phi follows, then phi is not the case. Phi doesn't follow. Only one of these things should follow. Either P or not P should be the case. So now phi and psi is true in a world W only when both are considered to be true. In the same way as usual disjunction rules, a conjunction is true only when both conjuncts are true. A disjunct is true, at least one disjunct is considered to be true. So these are all already there in the case of propositional logic. What extra that we are trying to talk about is something is considered to be necessary when it is true in all possible worlds. This is the idea which is carried forward. The idea which is taken from Leibniz works. So he is of the view that our world is considered to be one of the best worlds, best possible world. So there are many worlds, but our world that we are inhabiting is considered to be the best possible world. It is also considered to be another possible world. So now in this context, necessity of phi is true in a world W if and only if for all such kind of V's, some kind of worlds belong to some set of worlds W, and in all such kind of worlds V, this W has to be accessible to such kind of world V, and in that V your phi has to be true. If that is the case, then necessity of phi follows. In the same way, possibility of phi is true in a world W if at least there is one V, some possible world V, and in that your actual world is accessible to that particular kind of world V, and in that world V your phi has to be true. Simple thing is that for any given world your phi has to be true where W is accessible to V, and that V it is for any V. But in the case of possibility of phi, even if it happens for one possible world where your diamond phi is true, then it serves our purpose. So there is another way of defining the same kind of thing. Suppose if I write Vm possibility of phi W, you have to read it in this sense: possibility of phi is true in a world W with respect to a model M, and that is going to take a value T or 1. Usually we mention T by 1, false as 0. If and only if there exists some U where W is accessible to such kind of U, and in that U your phi has to be true. Whereas in the case of otherwise it is going to be 0. That means if W is accessible to U but P is false there, then it is going to be 0. Necessity of possibility of phi is going to be 0 because P is not going to be true there, P is false there. So in the same way, the necessity of phi is true in a world W with respect to a model M, that is going to be true or takes value 1, and if it happens for all such kind of U's where these W's are accessible to those U's such that your your u has to be true, Vm phi u has to be true there. That means in all those worlds phi has to be true. If w is accessible to u1 or u2 etc. In u1 phi has to be true, u2 also it has to be true. Otherwise it is going to be in any other case that you can think of where it is going to be true. So this is one important thing which we need to note. Suppose there may be a situation where no world is accessible to anything. For example, in this case let us consider some examples where for example, if it is like this is W1 and W2, and W2 does not consist of anything. So now here let us consider P is true in W1. Now you need to see that here W1 is accessible to W2, but we do not have any information about W2. So now if that is the case, if there is no world which is accessible from this world W2, then you need to know about this important thing, that is any formula that begins with necessity. It can be anything, it can be a contradiction or it can be any formula, P implies Q or anything. So that has to be true, whereas any formula that begins with possibility has to be false. So it is like as good as saying that there is a distinction between there exists some x and for all x. So the idea here is that if there is no world which is accessible from this W2, suppose if you are evaluating this formula with respect to W2, that means the necessity of P implies Q is true in a world W2. If there is no world accessible from W2, all the formulas which begins with necessity are going to be true, and all the formulas which begins with possibility of x is going to be false. In some of the examples you will come across these kinds of situations. So when the set of worlds are considered to be empty, that means there is no world which is accessible to that world W. Suppose if you are evaluating the formula necessity of phi with respect to such kind of world, then obviously it has to be true. I mean it has to be true, and in all other cases if you take the possibility of phi, it has to be false. So depending upon what kind of constraint you impose on frames, you will have different kinds of frames. These frames can be reflexive, transitive, symmetric, Euclidean, dense, etc., depending upon the constraint that you are imposing on the accessibility relation. So you need to note that again I was pointing out, repeating the same thing, that Kripke was he was talking about 4 levels of truth with respect to a world. If it is if something is true in all possible worlds, it is true, it is considered to be a valid kind of statement, a valid formula. And truth with respect to the frames, there are some formulas which holds only in reflexive frames, like T, necessity of P implies P, where this necessity of P needs to be taken as something like, if something is a theorem, all the necessary truths have to be true. So there is nothing wrong in it. But if you impose the same kind of thing in other kind of thing, then it may not hold. When in the case of you ought to follow the traffic rules implies that you actually follow the traffic rules, that may not work there. So these frame properties can be extended further, and then you can talk about irreflexivity, asymmetric, antisymmetric, all kinds of other things. Depending upon, you can impose more and more constraints, and then it will result in more and more logical systems. For example, in the case of 7th case, serial property is required for deontic logics. In particular, it is necessary that phi implies that it is possible that phi. So here is the picture that we have as of now. These are the most widely studied logical systems: K, D, T, B, K4, S4, S5, etc. The only thing you need to note is that K does not require any conditions. You do not have to impose any constraints on the accessibility relation, whereas T requires reflexivity relation, and B requires reflexive symmetric, K4 requires transitive property, and so on and so forth. S5 is the one which has all these constraints which needs to be imposed. For example, if you take this thing that necessity of P implies possibility of P, you ought to follow the traffic rules means you are only permitted to follow the traffic rules. You have to note that each and every modal operator comes in duals. If you represent something as necessity, you always have something which is represented by possibility, and necessity and possibility can be defined in one in terms of another. Necessity of P is defined as it is not possible that not P, and possibility of P is defined as it is not necessary that not. For example, you see here P, it is necessary that P implies it is necessary that it is necessary that P follows in S4, but it may not follow in K and even T, because it requires more than reflexivity, it requires transitivity. S4 requires reflexivity, together with that you require transitivity. For that reason, this possibility of P implies necessity of P. It is invalid in all frames, including the minimal modal logical system K. Once a given formula is invalid, you can construct, you can easily show it with the help of Kripke models, Kripke diagrams very easily. So these things will carry it forward, and then when we talk about semantic tableaux method, we will make use of these things in a better way. So in a nutshell, this lecture is all about we are talking about 4 levels of truths that is mentioned in Kripke semantics. One is truth with respect to the world, W. In that context, we have seen some problems. The only thing which you need to notice is that if there is no world which is accessible to the given world, then you need to view all the formulas that begins with necessity has to be true, they are true, and all the formulas that begins with possibility is considered to be false. And Kripke is also talking about truth with respect to a modal M, that is what is represented in this sense, A follows followed by M, and validity in a frame is defined in this sense. A is valid with respect to only this frame. Frame consists of set of non-empty set of worlds, set of non-empty set of worlds, and then you have an accessibility relation R, and if A is true in all interpretations based on that particular kind of frame F, then you represent it in this way. A is the logical consequence of F, or A is true in F. It is a frame that makes the formula A true. There is other way of reading the same thing. So validity in class of frames is like this. If theta is considered to be a set of frames, all kinds of frames, reflexive, transitive, all kinds of frames, we say that A is true in theta, the set of all frames, which includes reflexive, symmetric, serial, all kinds of frames. It happens for all such kind of theta. If F belongs to the theta consists of set of all frames. With this we will stop here, and then we will continue with the semantic tableaux method, with which we can talk about the same axiomatic systems, and then while constructing the while negating the formula and constructing the tree diagram for these things, we will come to know what kind of accessibility relation we need to impose on the given formula so that the branch closes. The branch closing means if not X is unsatisfiable, then X has to be valid. Thank you.